Cześć Zlondenu! Welcome to my talk using NATS for multi-cloud event streaming. I'm really happy to be part of this wonderful virtual event for Developers Live and thank the organizers for inviting me here today. First, I'll start with a small introduction. My name is Adelina and I'm a technology evangelist at Form 3. I've started at Form 3 only last month, so I'm still quite new. I've been a golfer since 2018, and I'm super excited to be here today as a speaker to share some of the really cool work we do with you all. Now that you know who I am, let me introduce Form 3 as well. The name Form 3 is derived from third generation cloud technology and a shortened version of platform, Form 3. We have some great customers who choose our payment platform as their payment processing solution. Form 3 was founded in 2016, and we've been growing and scaling ever since. We currently have around 260 employees, are a fully remote company, and hiring. So today we'll be learning about NATS. NATS stands for Neural Autonomic Transport System. Derek Collison conceived NATS as a messaging platform that functions like a central nervous system. Derek is an industry veteran and pioneer in implementing secure and large-scale distributed systems and cloud computing. He created NATS in response to the market need for simple, secure, and connective technology. NATS is an open-source messaging technology written in Go, and today we will be learning what it is and how we use it at Form 3. I will walk you through the Form 3 platform, then I will introduce you to the fundamentals of NATS and JetStream, after which we will be seeing how we are using NATS at Form 3. So let's get started. We've got a lot of ground to cover. First, we begin with the Form 3 architecture. Form 3 sits between financial institutions, our customers, and the external payments infrastructure, which defines the standards of interbank transactions. Our platform allows our customers to send payments to other banks. Our customers integrate with our Form 3 API, and then we take care of the integration with all the external payments infrastructure. The Form 3 cloud-native platform takes care of all the complexities of managing payments securely. The transactions we process are fundamental to modern life, like paying your mortgage, getting your salary paid, transferring money to your friends. Most payments in the UK are FPS or faster payments, and most payments in the EU are SEPA. Now that we understand where Form 3 fits into the vast payments world, let's have a look at our architecture. Our payment services integrate with our customers and receive payment requests. We achieve message fan-out with SNS and SQS. The core central payment services communicate all payments to all validation and gateway services, which then forward them to the corresponding external payments infrastructure. Our gateways do all the securing and mapping of the payments. We also have 2 data centers that we treat as an extension of our cloud platform, which process FPS payments. We have built our own private cloud from the ground up in our data centers, which present APIs similar to the public cloud provider. All this together is the core payments processing part of our platform and our topic of discussion today. Now, our current architecture has a few very strong pros. It is easy to add new schemes, and it is a managed architecture that scales well. The SNS and SQS pattern is simple to start with, scales well, and it is easy to secure and configure. On the other hand, there is a strong dependency on AWS architecture, and this strong dependency also sets the limits on our SNS and SQS limit of our SLA. We have noticed that there are a few spikes in latency of 300 milliseconds plus when our platform is processing high volumes. This is only bound to get worse as the number of transactions we process on our platform continues to grow. Finally, the AWS SLA is only 99.9% uptime for SQS and SNS. So this has real implications for a critical service such as our platform. So as I mentioned before, the SNS and SQS fanout was a really good place to start, but we found that it was time to evolve our architecture. NATS was immediately identified as a good candidate due to its out-of-the-box scalability. The fact that it is open source and written in Go made it immediately appealing to us, as Form 3 is a Go house. The NATS philosophy is simplicity, so the NATS server is easy to install and run. This was a great advantage as it had to run in our data centers as well. Let's have a look at exactly what NATS is in the next section. Introducing the NATS Fundamental Concepts. So Core NATS is a messaging service that enables us to send messages across clouds and technologies. It is simple, fast, and at its core is a fire and forget at most once messaging system. What this means in practice is messages are guaranteed to arrive intact and in order from a given publisher, but not across different publishers. NATS does everything required to remain available. However, if a subscriber is problematic or goes offline, it will not receive messages. With NATS, we can break away from the cloud and build a multi-cloud architecture that looks something like the diagram I have on this slide. Services can pass messages regardless of where they originated, and you can build a multi-cloud architecture. NATS supports 3 types of messaging patterns that we will run through today: pub sub, publish subscribe, queue groups, and request and reply. Each of these is a different paradigm that has its own use case with some overlap. Allowing for all 3 of these messaging patterns gives NATS great flexibility and functionality for various different use cases and systems. Okay, so let's begin with the publish subscribe. In NATS, publishers organize messages into subjects, which fundamentally represent an interest in data. A publisher sends a message on a subject, and an active subscriber listening on that subject receives the message. All messages are sent out to all subscribers with a matching subject, which you can see also on this diagram where messages 1 and 2 are sent to all subscribers, subscribers 1 and 2. Subjects can be matched either by full specification, like you see here, payment.uk, or by wildcard, which we will see shortly. This pattern is something like we might have with SNS, pushing out the same message to multiple subscribers, and is sometimes called fan out. Now, queue groups have multiple subscribers, but each message is consumed only by one. As you can see in the diagram, messages 1 and 2 are delivered to a different subscriber. To create a queue subscriptions, subscribers need only register a queue name. Once you join a group, your NATS will choose a subscriber by random, which will receive the message in question. Subscribers are configured only on the application level and not on the server configuration, making it really easy to create dynamic subscriber groups. Queue groups are therefore ideal for scaling services up and down, and NATS will take care of the queue administration. We can think of this pattern as multiple consumers sharing an SQS queue. Finally, the last messaging pattern is the request to reply pattern. And it looks a bit weird, but it uses the same pub sub pattern that we saw before. A request is sent, and the application either waits on the response with a certain timeout or receives the response asynchronously. This allows us to build acknowledges to messages when we need it, building in some reliability to the core NATS fire and forget. A request is published on a single subject, with a reply subject, and responders listen on that subject and send responses to the reply subject. Reply subjects are unique subjects called inbox that are dynamically directed back to the requestor. NATS even allows multiple responses to be received where the first response is utilized and the system efficiently discards the additional ones. So you could have subscribers racing to process the same message and only the fastest one winning, keeping your latency down. Now, I mentioned briefly about registering your interest either with a subject name or with wildcards. And here I will show you wildcards. There are two wildcard tokens, the star, which matches a single token, and the greater than wildcard, which can match multiple tokens and can only appear at the end of a subject. I've demonstrated their usage here with the pub-sub pattern. So on the diagram, subscriber 1 receives both messages as it matches one token with the star, and that token is the second one, UK. Subscriber 2 receives the messages as it matches multiple tokens with the greater than. In the greater than matches payment.uk.new. Subscriber 3 does not receive messages as the star only matches a single token, but the publisher publishes on a subject with two tokens here, payment.uk.new. Okay, we've learned about the NATS fundamentals from a theoretical standpoint, but now it's time to have a demo and see some cool stuff in action. As I said earlier, running the NATS server is really simple and easy. There are many options to running the server with Docker, Kubernetes, a package manager, or from source. We will be running it with the NATS server command, and it will expose a URL for clients to connect to. Furthermore, the NATS client library in Go is at github.com, nats.io, nats go. So our demo will follow the following pattern. We will start the NATS server, we will connect the publisher, then we'll connect some subscribers, and then we'll see the NATS magic happen. Without further ado, let's go to the first demo. So I've written some code that I'd like to share with you today. So what you see is I've created a payment struct on line 11, which has an ID, an amount, a currency, a sender, and a receiver. And then on line 23, I've written a very small method which generates a random payment with random amounts. Now let's have a look at our publisher. The publisher uses the flag package on line 17 to read a subject from the command line that we will be publishing to. Then on line 24, we connect to the NATS server using the default URL. And if we hover over it, we see that the default URL is localhost port 4222. Then once we've successfully connected to the NATS server, we start the for loop on line 31, which publishes random payments to the subject that we've given. And you can see that the publish is done on line 35 with nc.publish, and nc stands for NATS connection. And then we just send bytes of the random payment that we've generated. Okay, and now it's time for the subscriber. The subscriber is just as simple as the publisher. Again, we read from the command line what topic we should be listening to. Then we connect to the server exactly like in the publisher on line 22. And finally, we subscribe to the subject and we receive messages as it goes until it's time to exit, which we will do from killing it from the command line. So let's test this out in practice. I've prepared some terminal windows here. So we start the server with NATS server -d, and the -d only stands for debug because I want to show you some more verbose output from the NATS server. So we start the server, and as expected, it starts on localhost port 4222. Now, in the next window, we've got, I've prepared running the publisher. So the first publisher that I will run will start publishing to the subject payments.uk. So here we are, we start publishing payments, a random payment one by one. Then the second publisher will publish on the subject payments.pl. So one will have UK payments and one will have Polish payments. And finally, let's see what are subscribers in action. So the first one will start the subscriber and only listen to payments UK. And as it starts up, it starts receiving payments from the point that it was started up. So as you see, it starts receiving payments only from a message number 15. This is what fire and forget means. If you weren't there when the messages were sent, you won't be caught up on the server. Then the second publisher, or the second subscriber, will use the star operator. And then when I do this, you see now that we receive both UK and Polish payments. And you see the wildcard is matching on the multiple subjects that we've been publishing on. So that's it with two very small bits of code. We are able to start a NATS server and write publishers and subscribers, and they are connected and receiving messages. Now I will kill these subscribers. And let's go back to the NATS server and see what's happened here. What you see is that each time a subscriber and a publisher has connected to the NATS server, it started a client connection. And the NATS server keeps these connections alive with pings. Then finally, when they are disconnected, it knows that the client connections is closed. So let me just stop these. Let me just stop the publishing and then go back to our presentation so we can continue the fun. So I hope that you've been thoroughly amazed by the simplicity of NATS and how easy the client library is to use. So let's talk a little bit about the advantages of NATS Core. It has low configuration and it is lightweight. As we saw, it's so easy to start with just two small code snippets. We had a publisher and a subscriber. For some applications, the performance of basic NATS outweighs the potential losses of messages. Not all messages are that important. We can just resend them. But the at-most delivery model does have some drawbacks. If your subscribers are down, as we saw, the messages would never arrive. They're just dropped on the floor because NATS Core does not have any inbuilt persistence. This doesn't cut it for the financial transactions on our platform, where we cannot lose transactions into thin air. So we needed something else. It's time to try something else. As a response to the need for reliability from the industry, NATS introduced NATS streaming, or STAN, which is NATS backwards. And STAN traded some of the performance of NATS Core for message persistence. It was built with at least one delivery model in mind, and it is likened to TCP because it has the inbuilt capability of sending acknowledged messages for publishers and subscribers. And when the messages are published, they're persisted for some customizable amount of time so that they can be replayed to consumers if they haven't received them. The NATS streaming module acts as a client to NATS Core. As you can see in the diagram, the streaming module is a sidecar to the NATS server. We can view the NATS streaming client as a client to the NATS Core, but they do not communicate. So the application code connects to the NATS server, and then the NATS server connects to the streaming module, but your application code will never communicate directly to the streaming module. And the diagram came from the official docs. But as we enter the realm of message persistence, it's time to introduce the next step, which is JetStream. And JetStream was created to be a better streaming technology than we have today. It replaces NAT streaming and it is now the recommended option for persistence and message guarantees in your systems. JetStream is tightly coupled with core NATs through API, deployment, and operations. And unlike NAT streaming, JetStream is not a client to the NAT server. It is embedded into it. We just need to turn it on. And it has many features which were required of mature production systems, most notably the ones I've written here, which is at least once delivery, data at rest encryption, horizontal scalability, and persistence and message replay. But it does have a lot more features that you can go and you can read about in the documentation. So when you first arrive to the NATS ecosystem, the difference between JetStream and NAT streaming can be a bit confusing, as they seem to do the same thing. It's all about message persistence. However, there are some key differences. In NAT streaming, clustering provides protection against data loss, but it's only the leader that is the one handling publishing and consuming the messages. JetStream does not have this limitation. As we will see shortly, JetStream also provides the option to pull messages when consuming them, which is not something provided by NAT streaming. Finally, NAT streaming publishes messages to channels, which are internally managed FIFO queues made up of protobuf messages. They do not support wildcards, which was a huge selling point of NATs. So as you can see, JetStream has addressed some of the pain points that NAT streaming introduced. So therefore, that is why we should be using JetStream if you're looking to implement message persistence in your systems. So let's start looking at what JetStream actually is. One of the main concepts of JetStream is the stream. And streams define how messages are stored and their retention duration. They consume normal NAT subjects, and any message found on these subjects will be delivered to the defined storage system. You can do a normal publish to the subject for unacknowledged delivery, or you can send a request to the subject to the JetStream server, and you will get an acknowledgement reply. Relatively speaking, the stream is the most resource-consuming component. So it's very important that we are able to combine subjects, related subjects together, as you see on the diagram, where payment UK and payment.de are put together in one retention policy. You don't have to define streams to consume messages, but once your subject becomes part of the stream, it abides by the policies of the stream. And you can see here in the diagram that I've mixed and matched streams and regular subjects, because not everything needs persistence. For example, notifications might not be as important as payments for me. So I'll be happy to implement those on a NATS core subject, while payments are super important to me. So therefore, I want to make sure that they arrive. Makes sense, right? And the second and final concept of JetStream are consumers. And I mentioned before that they can be push or pull based. And JetStream will deliver messages as fast as possible to the subject of your choice if you push, or pull, you have control of when you receive the messages. And consumers track their own progress. They know what messages were delivered and acknowledged, and will redeliver messages they sent that was not acknowledged. When first created, the consumer sets a start position, either by specifying it or by default from the beginning by NATS. Naturally, if you don't define a stream, you'll only be able to create a push consumer because there is no storage in NATS core. And the last kind of configuration that you have on consumers is that they can be durable or ephemeral. And durable consumers will be able to continue consuming from the same place after disconnecting without you having to specify an offset. And ephemeral consumers will not, but you can still specify where to replay from. So I hope that makes sense. And again, we've looked at the the theory, but it's time to go back and have a look at the demo. So there is no JetStream server. JetStream exists out of the box, and we just need to enable it. And you either enable it by NATS server -js. So this tells the NATS server to enable JetStream, or you configure it with a configuration file like so, where -c says I'm going to specify a configuration file. And by default, the JetStream subsystem will store data in the temp directory. So it will create a new /tmp directory where you're running it from. And normally JetStream will run in clustered mode and it will replicate data. So the best place to store JetStream data would be locally on a fast SSD. So exactly like we've done before, we're going to do a short demo, and we're going to start the NATS server. We're going to connect to a publisher, connect some subscribers, and then hopefully you'll see that developing with JetStream is just as easy as developing with NATS Core, but this time you have message reliability. So let's go to the code. First, I will start by showing you my configuration file. So I specify a port 5222 because I don't want it to conflict with the previous port that I had of 4222. Then in the JetStream Online 5, I define a JetStream configuration, which changes the max memory store and the max file store. And it also changes the directory that I'll be saving my data locally in. And as you might be wondering why the port configuration is kind of just like hanging out in thin air and not in the JetStream configuration, but that's because the port configuration belongs to the NATS server, not to JetStream itself. So let's have a look at the publisher. Now I've changed the code slightly here because I've defined a JetStream URL on line 19, and I've already predefined a subject on line 16. And not much has changed actually. On line 26, we connect to the NATS server, and then on line 32, we define a JetStream context. So this tells the client, that we will be talking to JetStream and not to NATS Core. Then on line 38, I create a stream and send it the stream name and the subjects that it will be listening on with a wildcard, as you can see on line 40. Now, because I'm only running one publisher, I created a stream here because, I'm just making a shortcut for this demo. But remember that streams exist on the JetStream server, not on the publisher side. So if you were running multiple publishers, you wouldn't be able to create multiple streams with the same name. Instead, what you can do is you can use a Kubernetes configuration for your production systems, and you can find all of that documented in the NATS documentation. Then I defer a cleanup function on line 46, which lets me delete the stream once the publisher dies. And if I wanted to restart the same publisher, then the stream can be created again. And from line 56 on, it's all the same as what we saw before. We're going to create a random payment, and we will be publishing it one by one. The only thing to notice is that on line 60, we publish to the JetStream context, not to the NATS connection. And this is, again, because we are interacting with JetStream. So then I've prepared two consumers for you. First is the push consumer, which is exactly the same as what we saw before, where JetStream is pushing messages to the consumer as fast as possible. And on line 24, again, we connect to the NATS server, we create a JetStream context, and then we subscribe to it. So nothing different, except that we are interacting with the JetStream context and not the NATS connection. And the consumer poll is a bit different. So we connect to the JetStream server, we create the context exactly the same. And then on line 37, I define the pool subscribe, a pool consumer, and I pass in the monitor option, which says that I am going to consume without acknowledgements, so don't send my consumer acknowledgements. There are other options, which again, you can find in the documentation. Then on the cleanup, I unsubscribe from the stream because this is necessary for us to disconnect and say like, hey, I'm not going to be coming back to be pulling. And on line 54, I start the for loop, which will fetch a batch of 3 messages every 2 seconds. So, and then we will print out each of these messages to the console on line 59. So nothing too weird. I mean, I know the pool consumer is different because it's pulling in batches, but you know, it's nothing like mind blowing. It all makes sense, and it has all remained very simple. So let's have a look at this in action, exactly like we did before. Okay, so this is, I'm going to start the NATS server, passing it the configuration that we saw before, and again, the debug flag. So the server becomes ready and it starts on port 5222 as expected. Now in this terminal, I will run my publisher. And as I said, this time I've changed the JetStream publisher to not take in a subject because we will be creating a stream. So I've like hard coded the subject. So what it does is it starts up, connects to the NAT server and starts sending payments. And on the consumer side, first we start the push consumer. And what you see is that it immediately gets caught up from messages 0 to 6, and then we receive the messages one by one. And then I will start the pull consumer with the star. And we are, what happens now is we are getting caught up in batches of 3 messages. And once we actually get caught up, then we start receiving the messages one by one, exactly like we saw before. So there's no magic, but we have successfully implemented message persistence. And now no more payments are dropped in on the ground, in the ether, wherever you want to call them. The last thing I want to show you is that if I go back, so if I see the NAT server has been started in this JetStream folder. So I'm going to go back to the code and open up my my little like what's it called, like file viewer. And what you see here is that we've created a JS demo, folder, exactly like we specified in the JS configuration. And now the JS demo contains our messages stored as decided in the retention policy of the stream. And if I were to shut down the server, then all of these messages will come back, and anyone who hasn't received them, like an ephemeral consumer or a new consumer, will be caught up according to these messages that you see here. Okay, so this brings us to the end of our demo. Let's go back and really start talking about how we use the power of JetStream at Form 3. Okay, so we've been using NAT streaming as an event bus in our data centers, as you see here in the diagram with the physical data centers in production, and successfully delivering millions of messages. We are now going to introduce JetStream elsewhere in our payments platform. And the use case of SNS and SQS fan-out fits the NATS usage very well. So we can use JetStream as our event bus. The NATS streaming and JetStream clusters are bridged using NATS leaf nodes. Finally, the validation and gateway services are using pool consumers so that they have control of the rate at which they consume messages. NAT streaming is deprecated, but it is still being maintained until June 2023, so we have some time to transition to JetStream. So during our discussion of NATS and JetStream, I didn't go through all of the configurations available because there are many, trust me, and you can see that in the documentation. But one thing I wanted to showcase to you is the message deduplication. And our services are making use of JetStream as a data store. So we are going to use this configuration called the NATS message ID header. And NATS will discard duplicate messages directly on the stream in a predefined window. And this saves us message delivery and performing checks for duplicates on the database level. So this is like a huge performance gain for us, as you can imagine, because we won't even need to deliver these like duplicate messages that we're going to throw away on the application side anyways, right? And finally, we've mentioned clustering and horizontal scalability a couple of times already, but NATS supports running servers in clustered mode, and the cluster exposes a cluster URL for all of the instances, and the clients connect to this URL instead of the individual server URL that I showed you earlier on for ports 5222. The servers gossip and connect to all the servers they know, forming a mesh which can grow, shrink, or heal. And the NATS recommended amount of servers is 3 or 5 JetStream-enabled servers in a cluster, which balances scalability with failure tolerance. And of course, mixing server types is possible and even recommended to allow us to dedicate machines and keep costs down. So this brings us to the end of our epic journey with NATS and JetStream. So I just wanted to do a roundup of everything we've learned today. We found at Form 3, we found that NATS delivered on its promise of simplicity and ease of configuration. Running the servers was relatively simple. As I showed to you, we ran it from the CLI, but we have many other options such as Docker and Kubernetes. The Go client library is easy to use. As we saw in the demos as well, the code snippets were very small. And most importantly, NATS gave us the possibility to migrate our platform to cloud agnostic technologies and opens up a whole load of extendability and future proofing in our platform. But it's not just about the future. Let's talk about the metrics and the improvement that we see now, right? So it's difficult to compare metrics because it's a completely different message delivery paradigm between SQS and NATS. Generally, we did find that SQS was in the 50 to 500 millisecond range when delivering messages. I mentioned before, there were also some spikes of 300 milliseconds plus. But NATS actually gave us under 10 milliseconds delivery time. So it's a huge difference. And this latency of 10 milliseconds is subject to the servers being in regions that are not too far away from each other. So it's not like a perfect measurement. But since we host NATS, then we have the choice of where to put these servers. And finally, NATS streaming has persistent connection, so it's more or less real time. And this allows us to deliver messages between our data centers really quickly. And the last thing that I wanted to say is, why not Kafka? And you might think, why didn't they go for the battle-tested Kafka? So yes, Kafka is battle-tested, but so is NATS, which is currently deployed in some of the largest cloud platforms, including VMware, Cloud Foundry, and Siemens. NATS is definitely a lot more lightweight since there is no JVM, and it's easier to run as a cluster. And finally, as we've seen throughout this talk, NATS offers a lot of flexibility in consumption patterns, which is really important for us. This brings us to the end of my talk. I hope you've enjoyed learning so much about NATS and JetStream. And I just want to say, dzięki za wysłuchanie mnie. Thanks for listening to me. I will now open up for questions, and please make sure to visit our virtual booth as well.